Welcome back. We're now moving on to 21.2, Nuclear Equations. Here we're going to identify common particles and energies involved in nuclear reactions and write and balance nuclear equations. So, nuclear reactions happen when we have some changes of nuclei that result in changes in their atomic numbers or their energy states. So, similar to chemical reactions, but also very different. There's some different entities that are involved in these. They may have protons, neutrons, alpha particles, beta particles, positrons, and/or gamma rays. And you can see the different ways that we can write these shorthand. So these are what we use when we're balancing equations. Protons either have this 11p or 11h. The 11h is probably more common because it's showing more of, saying it's a hydrogen atom just without an electron. Neutrons are written as this 10N. Alpha particles can either be 42 helium or 42 alpha, but the helium is more common. Beta particles either be 0, -1 beta or 0, -1 E for electron. And then positrons are basically the opposite of beta particles, 0 +1 beta or 0 +1 E for electron. And then gamma rays are just this Greek gamma symbol. They don't have electrons or protons or anything to do with them. As we know, protons and neutrons are in the nucleus. Alpha particles are high energy helium nuclei. So that's why we use that helium abbreviation because it's got the 2 protons, which makes it helium, and then the 2 neutrons, then that gives it its mass number. Beta particles are high energy electrons. So these are just straight up electrons. And then positrons are positively charged electrons. And these are the most common form of antimatter. So antimatter is particles that have the same mass but an opposite state of another property. So in this case, positrons have the same mass but are in the opposite state of electrons. So they're opposite charges in that state. So you have a positive versus a negative charge. When you have antimatter that encounters ordinary matter, they're both destroyed, and then their mass converts into energy in the form of gamma rays. So, for instance, if we take our beta particle, which is an electron, and a positron, when they collide, they react to give us 2 gamma rays. Gamma rays themselves are photons, and they are from very, very high energy electromagnetic radiation. So these are produced when you have a nucleus that undergoes a transition from a higher to a lower energy level. Not to be confused with electron energy levels like we talked about in Chem 2A. So this is a different thing. Literally, the energies that are produced are millions of times larger than that of the electromagnetic radiation that comes from electronic transitions. So not electronic transitions from an electron changing energy states. This is from the nucleus transitioning energy states. And then there's a nice figure, 21.4, that gives you kind of a summary of the different types of particles and their symbols and what they look like. When it comes to balancing these nuclear reactions, they're somewhat similar to chemical reactions, but instead of showing a rearrangement of atoms, we're showing a rearrangement of nucleons. So the 2 basic rules here is that the sum of the mass numbers of our reactants has to equal the sum of the mass numbers of our products, and the sum of the charges of the reactants equals the sum of the charges of the products. So if we know the atomic and the mass numbers of all but one particle, we can identify it by balancing. And we're going to do that in the next example. So we're told the reaction of an alpha particle with magnesium-25 produces a proton and a nuclide of another element. And we want to identify the new nuclide produced. So we need to first go ahead and start writing what we know. We're told we have an alpha particle and we have magnesium-25, and we're given its symbol. So the alpha particle is this 42 helium. and we're told it's making a proton. So that's 1, 1 hydrogen, and then some other element. So we can put A, Z, and X. So we need to figure out what this guy is. So we know, though, that we need to have the same mass number on both sides of our arrow. So same total. So the mass number total on the left, we have 24 plus 4, so that's 28. So that has to be equal to 1 from the hydrogen plus A for this mysterious element's mass number. So that means that our A, oops, I'm sorry, 25, not 24 plus 4. I was like, wait, don't mind me. Oops. 29. There we go. So A must equal 28 then. So now we know A, and then we also know that our charges have to be balanced on each side. And so the magnesium, that 12, that's the protons, that's our charge for the magnesium. So we have 12 plus 2 from the helium. So that's 14, so that needs to equal some 1 plus Z. So then Z must equal 13. So that means our nuclear charge of 13 is aluminum. So our product then is 2813Al. This would be more of maybe a multiple choice question on an exam because it's pretty quick calculation. Or I might say, okay, what element is produced? And then you'd have to choose. And to end this section, there's some important historical nuclear reactions that I thought were interesting to talk about. The first one being the first naturally occurring unstable element that was isolated, and that was polonium. Polonium, discovered by Marie and Pierre Curie in 1898. Marie Curie, one of my personal heroes, is the first and the only person to win 2 Nobel Prizes in different sciences. So she won one in chemistry and one in physics. So she's pretty amazing. So what's happening is the polonium is decaying to form lead, and it gives off a proton, so it's an alpha decay. Then we have the first nuclide to be prepared by artificial means. So oxygen-17 was made by Ernest Rutherford in 1919. So we took some nitrogen-14 and bombarded it with alpha particles and was able to make this oxygen, and a proton is given off. Then we have 1932, the discovery of the neutron by James Chadwick. And so what he did is reacted some beryllium-9 with alpha particles to produce carbon-12, and then these neutrons were given off also. Then Emilio Segre and Carlo Perrier in 1937 made the first element prepared that does not occur naturally on Earth, and that was technetium. So they took heavy hydrogen, or deuterons, so you can see this mass number of 2, and bombarded that on molybdenum, and that produced 2 neutrons, and then this technetium. And then in 1942, the University of Chicago was able to do the first controlled nuclear chain reaction in a reactor. And there's a bunch of reactions that go along with this, but one of the many is uranium being hit with a neutron to make bromine-87, lanthanum-146, and some neutrons. And then these neutrons go on and react with other things, so it just keeps going and going, hence the term chain reaction.